Hello, everyone, and welcome to this evening's edition of the 2023 Von Karman series. My name is Nikki Wyrick from JPL's Office of Communications and Education, and thank you all so much for joining us for our wonderful discussion tonight, the universe of very cold, the James Webb Space Telescope, MIRI, and the Cryocooler. The James Webb Space Telescope, or JWST, launched about a year and a half ago and has taken some incredible images using infrared light. The optics and science instruments must be incredibly cold, especially JWST's mid infrared instrument, or MIRI. This is not possible without the cryocooler. Joining us as co host for this evening discussion is Caitlin Soares, the public outreach lead for astrophysics at NASA's Jet Propulsion Laboratory, presenting data through a creative lens and making complex scientific information accessible to wide audiences. Caitlin is passionate about exploring how the convergence of art and science can serve the public. Hiya, Caitlin. Thanks for being here tonight.
Thanks, Nikki, and thank you to everyone online for viewing our program tonight. NASA is your space program, and we wanted you to be involved in the conversation this evening. So please ask questions in the chat, and our social media team will pass them along to us. If for some reason you don't see the chat, please refresh your browser, and it should be there. We will try to ask as many of your questions as possible throughout our discussion tonight. And yeah, we're really excited to get into it. So back to you, Nikki.
Awesome. Thank you so much, Caitlin. As always, folks, if we do run into any technical difficulties or small failures tonight, we do ask for your patience and please do stick with us. We will get them sorted out as soon as we can. And now let's introduce our speaker for this evening, Dr. Konstantin Pennanen, who led MIRI's cryocooler development team through its design, build, test, and delivery to JWST system integration. He then led the MIRI project as it supported the larger JWST spacecraft element and observatory integration and testing. Now, currently, he is leading payload system development for SphereX, an all sky infrared spectral survey medium explorer mission. With a background in low temperature physics, he joined JPL in 2002. Wow, and worked on a variety of fundamental research, instrumentation, and flight projects. You might even say he has the coolest job at JPL. Hiya, Constantine. How are you this evening?
I'm pretty good, thank you.
Awesome. We're so thankful to have you with us today. So let's jump in right off the bat. What is the James Webb Space Telescope and what is its main mission?
Well, James Webb Telescope is the most recent flagship mission that NASA launched, and um, it's a iconic image you can see there on your screen right now. This is something that has been in development for over a decade, and it's going to produce results for many, many years to come. It is an infrared mission overall. What you can see there is an iconic primary mirror where you can see a reflection of cosmic structure behind. You can also see the very large diamond-like feature, which is the sun shield that blocks the light from the sun and from the Earth, exposing the telescope to heat. And that is really key to producing infrared images there. JWST will be obtaining data in the range of infrared wavelengths. Now, we will go into that a little bit more in just a little bit, but the main goals for JWST as a user facility, as a flagship mission, is to serve scientists for scientists to reach their goals. And the main capabilities that James Webb provides is really high resolution images in the infrared. And the science goals that come with that are looking at stars as they are born, at galaxies as they were born, as well as at planets around stars if we get to see them. And so let's go for a second to image 3. This one shows the history of the universe in a very compact way. It shows the going from left to right, it shows time spanning from the Big Bang, from the time that the universe came into existence, up to the present time, and over the initial period of time when this really hot protomaterial radiation coalesced into elementary particles, then atoms, then molecules, and eventually particles of dust, and then eventually started forming started forming stars, and then galaxies. And GWST will be looking back in time in a way, because it will be able to see some of the first stars that got created, the first galaxies that got created. It will also observe stars that are getting created now in spaces where there are large congregations of dust in space. It's an exciting facility, and it will serve the humanity for many years. Let's go to slide 4 for a second. And this is to address the question of what exactly how GWST is different. Here's the electromagnetic spectrum. You're familiar with the visible light, lights ranging from red to violet. As I just wanted to note something. If you look in the sky at night, and if you're lucky to see that, if the light pollution allows you to, you will generally not see any green stars, even though it's right there in the spectrum. But what you will see, either reddish stars or bluish stars or white stars. Red stars are the ones that are tilted towards the infrared or red part of the spectrum. Blue are on the shorter wavelength, on the blue side. But mostly that's because the light from stars is a mix of various colors. And of course, our sun shines nice and white, which is a combination of all of these colors. GWST is looking at light to the right of what is shown here in the visible spectrum. It's in the infrared, and it's spanning wavelengths from about 1 micron to about 25 microns for various instruments.
Yeah, so let's hit on that. You mentioned various instruments. JWST actually has 4 main instruments, but one of those JPL is responsible for, called the Mid-Infrared Instrument, or MIRI. So can you tell us a little bit more about how does MIRI work?
Right. So the mid-infrared instrument is the longest wavelength instrument on GWST. It spans the wavelength from roughly 5 microns to 25 microns, just over. And it has several functions. It has an imager, which is essentially a camera with which you can take pictures, and we will really spend most of the time today talking about that. It can also take spectra. What that means is that it can look at a specific object in the sky and then figure out what compositions of that spectrum show up in for that particular image. For the imager, for that object, for the imager, MIRI also has a number of filters that filter out light of a particular set of wavelengths. And by switching between those, it is also capable of taking images in different bands of wavelengths.
Yeah, so it's great to hear that. You've talked about how it's a little distinct because it uses this longer wavelength. I'd love for you to talk to us a little about image 5, if we could pull that up. Can you tell us what we're seeing here in image 5, Konstantin?
Yes, this is a great image, and this is coming as a recommendation of a project scientist, Mike Ressler. What you see on the right side is an image taken by another instrument on James Webb. That's NIRCam. You can see it's a lot of stars and galaxies there, actually galaxies mostly. There is a number of them, but you can see that a common feature for them is that you see that reddish tint and bluish tint and white, but you don't really see anything really in between. And what that really indicates is that NIRCam, it's taking essentially a thermal spectrum of various objects, various galaxies. What you see on the left is a MIRI image of the same field. And what I'd like to highlight is that you can see very stark colors, including greens. Mike Ressler would like to call it Skittles in the sky. It's a very, very apt analogy. The reason why the colors are so distinct there is that there are some chemicals in the dust that's produced in galaxies. Those chemicals are akin to car exhaust and barbecue smoke. Not very pleasant stuff, but those are aromatic hydrocarbons. Those light up at particular wavelength. And if you take an image with MIRI, that particular wavelength is highlighted. And some of these objects are moving from us at various speeds, at various velocities. And as they move away from us, the light from these galaxies is redshifted. So it's getting longer in wavelength. But the combination of that is that you can see galaxies that are closer to us are looking more bluish. Galaxies that are further away are looking more red, but they also have very, very distinct colors.
Yeah, I mean, so we've talked a little bit about this longest wavelength and that we can see these more interesting things. And you mentioned very briefly just then we can see through this dust. Why do we want to look through the dust? Why is that something we want to be looking through?
So let's actually move to image 6 for a sec, and I'll speak to your question as well. Dust obscures light as it comes from galaxies, and particularly in nebulae. When you have dust, you cannot really see material light from behind there. And so if you take an image invisible or near infrared, you would able to see only the light from objects that doesn't pass through that dust. And then in the infrared, in the mid-infrared, you get more of the light coming through the dust. And you can see objects that you otherwise wouldn't. Stars that are hidden otherwise in places that they are born in those nebulae. And then on this image, what you see is a debris disk. What you can see here is effectively a solar system that is in the process of getting born. This is really probably how our solar system looked 4.5 billion years ago. You can see there two distinct rings. The outer ring was something that was seen before JWST launched for decades. The inner ring is something that was possible to see only with JWST and MIRI basically in the last year. And what you can see there, really what that really corresponds to in our solar system, the outer ring is looking like an Oort cloud. It's similar to our own Oort cloud. That's Pluto orbit and beyond. And the inner ring here corresponds to what we have for the asteroid belt. And the fact that these are really well defined, that really means that those dust particles are interacting with gravity centers. So there is probably something that looks like a planetary system in there. It's again, I mean, it's one of the things that we see with the infrared, and the fact that the rings are so bright, that indicates that there is some heat dissipating in there. That means that those particles are colliding with each other all the time, producing a little bit of that heat.
Wow, that's incredible to think that just looking at this image, like when we talk about our own solar system, we could only see what is essentially as far out as Pluto and the Oort cloud. But now with MIRI, we can see so much more detail in this image. I just think that's amazing. So we talked a little bit about the dust and we talked a little bit about MIRI, but this instrument, it does great things, but it needs to be incredibly cold in order to work, right, Konstantin?
That's correct. And let me tell you first why. the infrared, what we really see with the infrared is heat. If you, I mentioned wavelengths of light between 5 and 25 microns for MIRI. Right in the middle of that is roughly 10 microns, and that is the wavelength at which all of us are radiating heat. So as we walk around, most of the spectrum that's emitted from human bodies at roughly 300 Kelvin is at about 10 micron wavelength. What that really means is that if we launch the telescope at 300 Kelvin, we would be blinded by the telescope itself. We wouldn't really see anything. So the telescope needs to cool off. That's one. And then in order to detect the light at this wavelength, it all has to come down to a detector. Let me share an image, image 12, please. That's an image of one of 3 MIRI detectors. It really is very similar if you open up your camera, if you have an ability to do so, to remove your lens. You will see something looking kind of similar to that. It's about an inch by an inch size square, and it senses, in this case, infrared. The technology in order to see infrared of this wavelength is such that the detectors need to run really, really cold. And for us, the temperature at which the detector run need to be below 7 Kelvin. And MIRI runs its detectors at a temperature of roughly 6 Kelvin. So for both reasons, for detector technology reasons and not to be swamped by the light from the instrument itself, everything needs to be cold.
I get that it needs to be cold, but it's kind of cold in parts of space. This needs to be even colder than that, right? What's the difference between passive cooling, which is used by a lot of the other instruments on board JWST, and the active cooling used for MIRI?
That's right. So for the longer wavelength between 1 and 5 microns, a combination of more tolerance to this background and more tolerance to or different detector technology. Those detectors can run at a temperature of 30 Kelvin and even above that. And that temperature is possible to meaningfully achieve with passive cooling. And what that really means is that um, if you look into the deep of space and you don't have any heat sources nearby, and you shield yourself from the light and heat of the sun and Earth and Moon, you will eventually reach the temperature of the microwave background radiation, which is 3.7 Kelvin. So you can passively cool. You can cool to 30. To get to a temperature of 5.9 or 6 Kelvin, that is not really meaningfully possible. Just very tiny amounts of heat dissipation that we need to have in the detectors, and attempts at passive cooling would just take it over the edge. And therefore, we need to do active cooling.
So, Constantine, just to clarify, the passive cooling is very similar to what you were talking about with the sunshade earlier when we looked at that first image, right?
That is correct. Yes. So you put the sunshade to block yourself from the sun, and then you put something that's painted black, dark, that does really good job of emitting in the infrared. You point it to the deep of space, and that's how you get to those temperature of 30 Kelvin. And other missions rely on just that method of cooling. Many missions do, including SphereX that you heard a little bit earlier. But for MIRI, that's not enough. For MIRI, we need to do active cooling. And let me jump into what that is. In order for us to cool MIRI, we use a cryocooler. And Cryocooler is a fancy name for a refrigerator that works really, really cold. Cryo stands for cold. Cooler means for cooler. If you, I'll show a picture. Can we go to image 14, please? So what you have here is sort of the heart of the MIRI cryocooler. It's several compressors. What you see there in those cylinders is pistons that move back and forth. Um, some of them at one of them at 30 times a second, another one at 90 times a second, and it compresses gas and then expands it. So as gas is compressed, it gets heated up. You take away that heat and radiate it away into space. And after that, you expand the gas, and then that cools that gas off a little bit more. And then you repeat that many times a second, and you do that in several stages. You take the first stage, you cool that to something like 150 Kelvin, next stage to 50, next stage to 18. And the final stage, you get to something like 6 Kelvin. It's a little bit more complex than that, and if you want to look for more detail, just use your web browser and search for MIRI Cryocooler. You'll find a lot more. But generally, that's what this is. It's the most awesome refrigerator in space. It consumes power. If you're familiar with incandescent light bulbs, we used to have those. It uses the roughly light of power of 2 light bulbs. It's just over 100 watts, and it achieves the temperature of 6 Kelvin.
Konstantin, this is the most awesome cooler in space, that is for sure. But how does something like this get designed and built?
Well, that's an enormously complex process and long process, and something that involved a very large number of folks. The concept for this cryocooler predated GLBST concept and has been in development for a while. It's a team effort. The cryocooler was developed at Northrop Grumman. The effort is led by JPL. What is happening is that we start with the design. We demonstrate that the design works on the prototype. Then we start designing flight hardware, and then piece by piece build it up, and then test it thoroughly. We go through environmental testing, which means that we expose the hardware that we build to equivalents of rocket launch and the deep of space for thermal reasons. It's a rigorous rigorous process that's common to many NASA missions, and Cryocooler had to experience that.
So, Konstantin, why don't you tell us a little bit more about the development? And let's pull up image 15. And can you tell us what you see on that image?
Right. So this is the last stage. This is the heat. This is the cold head assembly. This is something that is mounted right next to the instrument, to the optical bench of MIRI. You saw that detector. So that detector would be within a couple of feet from this coffee can. This portion of the cryocooler is right next to the instrument, which also means that it's if you remember from image of GLBST, let's actually go to image 2 for a sec. You can see here the primary mirror. What we are talking about is what's behind the primary mirror. What's happening really for GLBST is light bounces off of the primary, hits the secondary. That's the thing that is sticking out, supported by those 3 struts, and then hits a tertiary that is in that extended knob there, and then the light is distributed to a number of instruments. All of those live behind the mirror, and that's where MIRI is one of those instruments. So what you saw, and let's go back to image 15. What you saw is the cold head assembly that eventually got integrated into the integrated science instrument module. Let's go to image 17 for a second. What you see here, and you just saw that coffee can by itself, and now this is that same cold head assembly that is sitting next to MIRI optical bench. MIRI was the first instrument integrated. We're very proud of that. Um, and here you can see just moments after this cold head assembly got installed onto ISIM, Integrated Science Instrument Module. There's a little bit clearer picture on image 18. Yeah, what you can see here is just before. Well, you can see here the same heat exchanger stage assembly, cold head assembly, as well as a somewhat opened up image of MIRI optical bench. I do want to mention one thing. I had mentioned that GPL was responsible for MIRI. GPL was responsible for MIRI from NASA perspective for the US segment of this work. But MIRI is an international collaboration with ESA and MIRI European Consortium. It's a 50-50 partnership. European partners built up the optical bench, and then they included GPL built detectors in that optical bench. And then GPL was responsible for the detectors as well as the cryocooler, and the cryocooler work is what I'm describing here.
So, Konstantin, since you brought it up, it takes a whole bunch of people to do something like this. So, what was it like, the team behind the scenes that was able to build both MIRI and the cryocooler?
I think this is the most amazing, really multi-year, multi-institution development. It spanned, of course, many years. Was trying at some point to count number of people who touched MIRI flight hardware, and the number eventually goes into thousands. If you count all of the components that had to come together, and the MIRI cryocooler, I already mentioned Northrop Grumman. We also had contributions into the hardware, both from JPL and from Goddard Space Flight Center. But the team is large, and they had to follow the hardware from the design stage all the way into the integration. And there are a number of interfaces between different pieces of hardware. What that means is that when you build something like that, you need to know that it's going to fit when you put it into the next thing, which means that you need to have people talking to each other all along, making sure that that goes smoothly. And that goes not just to mechanical integration. It also means that you have to agree on how the power is going to be used, how the data is going to be transmitted. All of those details are quite complex, and it's amazing how this came together as a system at the end.
Absolutely. And if we could pull up image 23 real quick, this is only a small fraction of the team that you worked with, right, Konstantin?
That's correct. So this is the a part of MIRI Cryocooler. This is the compressor assembly. Just before it got shipped from Northrop Grumman to JPL, and the team that is displayed there is a combination of JPL folks and Northrop folks as we worked together. I think this was a significant development for both entities, and the team was extremely dedicated and very skilled. It's for many of us, it really is an accomplishment of a lifetime. It's quite amazing.
So, Konstantin, I want to leave plenty of time for the audience questions, but I've got one last question for you before we open it up to them. What do we expect to see from the cryocooler in the coming years?
Well, we expect the cryocooler to continue chugging along. There is nothing in the cryocooler that is limiting its life. Eventually, electronics in space tends to deteriorate and die just because it's exposed to radiation. So at some point, that will start happening. So far, things are behaving really well, and for JLBST in general. The life really is limited by the station keeping maneuvers that the amount of fuel on board is going to eventually limit. But it's not going to happen for years and years to come. I did want to show how this all comes together. Can we go to image 25 for just a sec?
Yeah, absolutely.
So this is the integration of the observatory overall, and in the middle of that image, you can see a little harmonica looking like shiny object, and that's just a little portion of the cryocooler that is sticking out through there. If we go to image 26 for a sec, you can see that cryocooler getting moved from below the observatory to be integrated, and eventually this hardware had to be connected. The two different pieces of Cryocooler, the one that's close to the instrument and the one that is running in the spacecraft bus, they needed to be tied together, and that was happening at the very end of the integration. With that, I do want to show when the work was complete. Can we go to image 27 for a sec? So this is the team after the Cryocooler got integrated, and we just happened to be at Northrop Grumman when they were also doing the test deployments of the MIRIs. And this is just a wonderful picture. But my favorite picture, and let's go to image 28 for a sec. Is this one not because of the face there, but I asked for this image to be taken because what you see there is what's behind the curtain, behind the mirror. This was the time after the Cryocooler got installed into GWST. We needed to make sure that all of the connections, all of the pneumatic connections, I mentioned that the gas that's getting compressed and expanded, that none of that gas is leaking out. And so this is after we made final integration of the Cryocooler, we needed to do that leak check. And that work is happening on the background right here. This was, I think we were the last to be at the heart of the observatory to perform that measurement. And when we were done, we were very, very happy.
Constantine, I have to say that is also my favorite image that you have pulled up so far this evening. They have been asking a lot of great questions online. So, folks, thank you for those questions. Caitlin, what are they asking?
We have a lot of questions here, Constantine. I'm going to start with kind of an umbrella question, but can you speak a little bit to what the key science objectives are of the James Webb Space Telescope? And to add on to that, how is MIRI supporting those objectives?
Right. So the key objectives would be to look at the first light from the universe. This would be the light from the first galaxies, the formation of first galaxies. We're beginning to see some of those results already. There's an objective for JWST is to be able to observe birth of stars and planets. That is also something that already has been happening in the last year. Last and more recent addition to the set of goals for JWST was looking at exoplanets. Sort of the variety of solar systems where you would have exoplanets that our understanding of that grew in size quite a bit in the last few years, and JWST certainly is now making it its focus.
Great. We have another question here. Farrell on LinkedIn asks, what are some of the surprising results from MIRI observations so far? Could you speak to one or two of those?
Well, so I do want to say a couple of things. I am an engineer, although I am very, very curious about the science that MIRI is going to achieve. But I do want to say that one image that I showed about that inner ring, that was a surprise. The Skittles, that was a bit of a surprise. It's just looking at the variety of that. Of that. That was really good. I do want to show something. Can we go to image 9 for a sec? So in the image that you're just about to look at, image 9, what you can see was one of the first things that that folks very quickly found even during the commissioning of the Cryocooler. Commissioning of JWST. This was looking with MIRI at the same part of the sky as another mission, Spitzer, looked at before. This is around 8 micron wavelength. This is basically the difference. You can see what MIRI can do. It looks at details. MIRI and JWST overall. It looks at objects with far more detail, and that's where the focus really is to find places, to observe things with much more clarity than before.
That's an awesome
Great. We
image.
have another question.
Yeah, great.
Yeah,
We've got time for
we have
some
a lot
more.
of questions. A lot of questions coming in. I don't know if you want to answer this, Konstantin, but I'm going to throw it at you. What would happen if, for any reason, the cryocooler got damaged or was in need of repair?
Ooh, yeah. So unlike Hubble, there is not a plan for a service mission. So what really needed to happen is for us to build it in a way that it's robust and reliable. I mentioned electronics that potentially will get damaged by radiation. We actually have two of everything there for electronics. So if we have a particular component that failed on us, we have an ability to swap out. I mean, to switch out to a second one of the same. Of course, there are other possibilities. Nightmares are built of those things. We can have a micrometeoroid hit just in the wrong spot, and we can have helium leaking out, or some other type of damage. We were careful to calculate what those effects might be, and build some design features that protect from most of that. So we should be good, sorry, no plan to repair.
All right. And speaking of design features, what types of metals, lubricants, et cetera, are used for the cryocooler components to function at such a low temperature?
Well, that's really interesting. So because we have to design for very long life, cryocoolers, these very reliable cryocoolers, they are now built without lubricants. They are built with very, very tight tolerances mechanically, so that you would end up with not something that rubs against each other. It's a difficult problem, but it has been for the most part solved. So no lubricants. Again, there are no features here that are really life limiting. I think everything that we thought mechanically through makes us think that it's going to last.
Great, thank you. That question came from Johnny on YouTube. This one comes from Jorge on Facebook, who's asking, actually a few folks have asked this, where does the heat from MIRI go? Like what happens to the heat as the cryocooler is bringing the temperature down?
Oh, that's a really excellent question. So the cryocooler takes away heat from one spot and has to dump it elsewhere. So it takes away the heat from the instrument, and through these stages of cooling, it pumps it out eventually to radiators that are on the warm side of the spacecraft. It's actually on the sun-facing side. And so the heat is getting rejected at roughly room temperature. This is for convenience of testing, but also it's something that we know how to reliably work with. So yes, the heat is getting pumped from the cold region into warm region, and that takes energy. That's what those 100 watts or so of power are needed for.
Sounds like a lot of work for that cryocooler. We unfortunately we only have time for one more question. We have a lot of great questions in here. We have time for one more. Ronald on Facebook asks, I am an 8-year-old and I'm learning to be a scientist. My ultimate goal is to work for NASA when I'm grown up. Could you share any advice to help me achieve my goal for working at NASA as a scientist?
Oh, what a great question. Um, what I would say is that follow your heart, be curious, find what appeals to you, and it can be a lot of things. It can be various areas of science, physics, chemistry. Um, it can be something that is engineering field of some sort. So you can go and do mechanical engineering, electrical engineering, thermal engineering. Uh, many fields lead to a path at NASA and at a mission like that. Again, out of those 10,000 people, the variety of fields that folks came in with, and I don't want to omit people who do the mechanical work of machining parts, putting things together, basically technicians that solder parts in place. Those are callings that also are key to success here.
Thank you for that wonderful advice. And as Caitlin said, unfortunately, that is all the time we have today for those wonderful questions you all have been asking out there. I want to take a moment to thank our speaker, one of the coolest guys at JPL, Dr. Konstantin Pennanen, for joining us to discuss the cryocooler and MIRI. Also, thank you to our wonderful questions co host, Caitlin Soares, and everyone working behind the scenes to make this possible. To all of you watching at home, thank you so much for taking the time to join us each and every month. And by the way, if you did miss one or would like to revisit any of our Von Karman talks from the past 5 years, they're all available on JPL's YouTube page. Please do also join us next month for our discussion with Dr. Stacy Boland, Vital Work to Benefit All Humankind. Thank you so much, everyone, and we will see you in July.